This video is going to continue to look at converting polar and rectangular equations. So if we're given the following polar equation, r equals 2 cosine theta, we want to convert this into a rectangular equation. And if we recall, we have x is going to be equal to r cosine theta. We know y is going to be equal to r sine theta. And then, of course, we know that x squared plus y squared is equal to r squared. So if we're looking at using these equations to substitute, again, we want to get rid of r and theta and change everything in terms of x and y. Now, pay close attention to this one because there's a couple things we could do to approach this one. We have r equals 2 cosine theta. Well, if we look over here, it would be really nice if we had r squared, because r squared is simply x squared plus y squared. So over here, all we have is an r to the first power. Well, how could we make that r squared? Well, one thing we could do is we could actually square both sides. Now, let's see what would happen if we did that. If we were to square both sides, we would end up with r squared equals 4 cosine squared theta. And that would help us here with the r squared. However, though, over here we have 4 cosine squared theta, and we couldn't substitute for the cosine, which if we did that, we have x equals r cosine. We could, of course, change cosine theta equals to x over r, but if we substitute x over r in for the cosine, we're still having an r back into the equation. So, as we could square both sides here of the equation, there's another way that we could end up with r squared. And that is, instead of squaring both sides, what if we were to multiply both sides of the equation by r? So then we would have r times r is r squared. And then over here we would get 2 times r cosine theta. So the nice thing here is we have the r squared, which is going to go to x squared plus y squared. So that's from over here. But then notice we have r cosine theta. Well, that's exactly what we have over here, and that is simply equal to x. So therefore, we can substitute x in for all of this, and we're left with 2x on the right side of the equation. So here, we've actually converted the polar equation into a rectangular equation, and now the only thing we have left to do is possibly to rewrite and simplify the equation. And here, to do that, we have an x squared and a 2x, so I'm simply going to move the 2x over, so we get x squared minus 2x. And then, of course, we have the y squared, and we have the equation equal to 0. Now here, we could actually go about simplifying this by completing the square. Now, keep in mind, if we're going to complete the square, the x squared term here has to have a coefficient of 1, which it does. So then, in order to complete the square, we're going to take half of this value here, so half of a negative 2, and then we're going to square that. So half of a negative 2 is a negative 1, and a negative 1 squared would be positive 1. So we're going to add 1 here to complete the square, but if we add 1 to the left side of the equation, we have to add 1 to the right side. So now we have x squared minus 2x plus 1, so that will factor to a perfect square of x minus 1 squared, and we bring down the y squared, and the equation is equal to 1. And what we'll notice here is we end up with a circle. This is the equation here of a circle, if you recall, x minus 1 squared plus y squared. We have this is a circle where we have the center is at 1, 0, and we have a radius of 1. So the r equals 2 cosine theta is going to give us the equation of a circle, and then of course the rectangular equation would be x minus 1 squared plus y squared equals 1. All right, so let's look at another example here. What if we're simply given the equation r equals 10? And once again, we want to change this into rectangular form. And just to recall, we have x equals r cosine theta, y equals r sine theta, and x squared plus y squared is equal to r squared. So once again, it would be nice if we had r squared. Well, if we tried to use the technique we did before, if we multiply both sides by r, we would end up with r squared equals 10r, which is nice for the r squared, but over here then it gets a little more complicated substituting in for r. So a little bit easier technique here would actually be to square both sides, because then if we square both sides, we get r squared is equal to 100. That way the 10 is only squared. We're not introducing another variable that we do not need. So here, as opposed to the previous example where it was better here to multiply both sides by r, for this particular equation, it works a lot better to square both sides, and we get r squared equals 100. And then of course here, r squared we know is equal to x squared plus y squared. And here we have the equation of our circle. X squared plus y squared equals 100. All right, the next equation is r equals 2 secant theta. And again, we have x equals r cosine theta, y equals r sine of theta, and x squared plus y squared equals r squared. Well, if we notice here we have the secant theta, which it's probably going to be a lot better if we change it in terms of our sine or cosine, and we know that here secant theta, we could simply rewrite that. That's reciprocal for the cosine function, so we could write this as 2 over cosine theta. And now if we want to get the cosine off of the bottom, out of the denominator, we could multiply by the cosine. And in doing so, we're going to get this cosine cancel off the bottom, but then on the left side, we end up with r cosine theta, and r cosine theta is simply equal to x. So therefore, we get x equals 2. So there we end up with the equation of a vertical line at x equals 2. So r equals 2 secant theta. Again, we have a secant. Whether you have secant or tangent or possibly cosecant, you're probably better off converting that in terms of sine and cosine, because over here, that's what we have in order to substitute into the equation. All right, so here you have a couple examples of what we can do to change our polar equation into a rectangular equation. So keep in mind, once again, sometimes it's good to square both sides of the equation, like this one here, or the previous example, sometimes it may be better to actually multiply both sides of the equation by r.